Okay, so before we start, maybe you don't have any of your group member because that person went to home because of the long holiday season. So if you don't find your group member currently, then you can join nearby group, for example, 9. Do you have, how many of you in group 9? 3? Okay, so 10. Are you in group 1? Okay. So if you're alone in your group, then you can group up with the group next to you. Okay. Okay, so we're going to uh, cover two slides today because we have a holiday on next Wednesday. So let me walk through the slide that we saw before, and I'm going to walk us through the project 2 about the calculator. And okay, so I forgot to mention this. I'm going to give you the paper again. So if you change your mind on the topic of your first project, then you can cross out your name and then put your name on your new topic. If you don't have any change, then you can just pass it to the next person. Okay, let's look at the slide here. So this is our second project. So we need to understand how to implement function using power function, a power series. So I explained what the power series is. It's basically of this form. So whenever it's a series of power functions, and whenever you define a power series like this, it's important to know the radius of convergence. It always converges at the center. If you plug in C in the place of X, it's always 0. But I mean not 0 because A0 is here, so it's always A0. But if you want to know how far can I move from the center until the series diverge. So for example, if you have this power series, you can see that this is the graph of this power series, considering this as a function of x. And you can see that the value of function is going to diverge near 3, because this power series has radius 2 from the center 1. So it can move from minus 1 to 3. And okay, so one way you can define a function is a power series. Another way of defining function like a square root is using a sequence. So I used a recurrence sequence with a recurrence relation like this. So you need the previous element, an, in order to find out the next element, an plus 1. So this is how you could implement that in the Python. And okay, so how you can, there may be two different ways of defining function. For example, in the exponential function, you can define a function using a sequence. So here it's similar to the sequence of natural constant, but you have x in here. Okay? You have x in here. So it's a little bit different, but that's a definition. And you could also define an exponential function using power series like this. So both definitions are fine, but I prefer the first one purely because of a mathematical reason. Because if you define the exponential function using the power series, it's very convenient in many reasons, but it's hard to talk about the differential and differentiabilities and so on, because this is the material that we're going to cover probably later. If you define the function, exponential function, as a power series, how would you define a differential of the power series? Because you need to take the difference, and when you try to take the difference of infinite sum, now you have to consider the notion of uniform convergence and so on. So it's very complicated. You need lots of mathematical, theoretical backgrounds to talk about the differential. So I prefer simple definition as a series. So this one, the script here is theorem. It's the implementation of exponential function using the first definitions, right? This one, okay? Okay, so how do you, the next function that you might try to implement is the log function. Now, the definition of log is the inverse of exponential function. So whenever you try to find the log value, you need to trace back the value of exp and then try to find out at which point does that exp value is achieved. So for example, if you want to find log x, you want to look up the graph of exp and consider that your value of exp is x, and you're trying to find the y right here. So now the role of x and y are switched because we're looking at an inverse function, so that this y is going to be the log of x, right? So we need to use some method finding the root of this equation, exp y equals to x. So this is given, x is given, right? So this is known. Y is what we want to find. This is not known. So in some sense, this is an equation with an unknown variable y with a known constant x. So whenever you have this kind of situation, the problem is about finding the solution of this equation. So one method you can use to find the solution is bisection method. So you keep bisecting the interval that you first guess that this y lies in, and then when you keep dividing the interval into half and then tracing which half does this y would lie in. So you just keep the interval, half of the interval, every time that you guess that your y lies in, and then you keep taking half of these intervals. And of course, there's another way of calculating the log. So definition of log is the inverse, but calculating is different issue. So if you want to calculate the log, you can use the power series again. So this is the power series that predicts the log value. However, the problem of the first power series here is that it has the finite radius of convergence. So what is the radius of convergence? So let's think about the convergence test that we talked about yesterday, last time. So I want this to converge. We can use either a ratio test, maybe ratio test is better, or other test if you want. Then ratio test says if you have a common ratio, so if you take the ratio of the consecutive terms, then n and n plus 1 will limit to 1. So all you have is the x minus 1 to the power of n plus 1 over n, x minus 1 to the power of n. So basically you'll get with the ratio of x minus 1 absolute value. So if that ratio, the limit of ratio, is less than 1, we know that the series converge. And if it's bigger than 1, we know it diverges. So x minus 1 less than 1 converge. X minus 1 bigger than 1 diverge. It means that radius is 1. This one is the radius, right? So it means immediately that you can move your x up from the center 1 up to 1. So your interval of convergence is 0 to 2. So if you plug in value outside of this range, then you will get an infinite number, like a diverging series. But log, of course, it's not defined on the negative real number, but it's defined on any positive real number. But this series only works in this finite range. So how could we get the value of log for the x bigger than or equal to 2? So in order to compute that, we need to use a little bit of adjustment here. So you can think of your log x as the sum of these log values, okay? So here, t is the number computed from the value x. In that case, t always lies in between minus 1 and 1, right? So log 1 plus x, 1 plus t, and log 1 minus t always lies in 0 to 2 range. But you can take any value of x you want. So here, no matter what value of x is, t always lies within minus 1 and 1, right? Minus 1, yeah, almost minus 1 and 1. So you can take any value, a positive value for x. So if you actually you can take the power series of log 1 plus t and log 1 minus t again. After we learn about the power series, Taylor series, you can actually do that. Then you can you can convert that into a power series like this one. So this is another way of computing log instead of a bisection method. Okay, so we talked about this before, but anyway, so cosine and sine are functions defined geometrically. However, it's hard to find the value for the sine and cosine for general angle theta. So in order to compute the sine and cosine, we need to use the power series, like this one. So this is actually a Taylor series. It comes from the Taylor series we're going to cover in the next class. So you might want to remember this formula because this is important. And so this is how you could implement your power function for sine and cosine into the Python. Now here's the part which make the calculator. So I want a program, when I run my script for calculator, I want the program looks like a normal calculator, not the fancy one, not the like graphing calculator, but just the calculator with one screen which gives me a number and also lots of buttons that could used for the arithmetic computations or root or sine, cosine, exponent, so on. So imagine something like not high-tech graphing calculator, not that high-tech engineering calculator. So what we're going to do is we're going to take the input of number or a function as a text. So if the inputted text is the number, then we can replace that number as our current number that stores in the memory. And then if it's the function, if it's the text about a name of a function, then we can try to compute the previously inputted number. And we try to compute the function at the point, at the value which is previously inputted. So here are the list of functions that we're going to implement. Basically the same function we introduced before, the square root and log, sine, and cosine. So I'll mention that your additional task is to implement more functions than these ones. And for technical reason, we need to implement arithmetics. Arithmetics as a separate function. So I'm going to introduce 4 arithmetics. So addition and subtraction, multiplication, and division. So the reason why I'm defining these arithmetics as a new function is because I'm going to convert the inputted string of these symbols into an actual function. So I need to, map this string of characters representing the arithmetics into to the function that I want, that actually does that arithmetics. Because I cannot use this symbol as my, name of a function. So name of a function must always be an alphabet. So that's why I'm using a different function, separate function. So here is the basic algorithm, but we're going to walk through every steps together. So you can see that the whole program is nested in big loop here. So while is a one way you can make a loop. Instead of for, while takes terminating, not terminating, but it's a condition that keeps the loop proceed. And I put 1, meaning that it's always true. So this loop will proceed infinitely many times. Okay, so infinitely. So each time I'm going to take an input and put it into the variable called expression. And I'm going to try to convert that expression into a number. That's what I did here, right? And I put it in the try command, try keyword here. That means I tried this. I mean, basically it's running this line that variable is going to contain the data that is converted from the string expression as a float data type. But what I do here is I'm trying to take or detect an exception, whether exception has occurred. So I just try to convert the expression, but my expression, the inputted text, may not be a number, right? I could input a text, any text. So if that's the case, then converting into float is not succeeded. However, the value will be, the output of the conversion is going to be 0 or none, whatever that value is. The variable val will contain some data, but it's not what I intended. So therefore, in that case, if the value error occurs, that means the conversion is not succeeded as I intended, then it means that the expression is non-numerical string, right? So then I have to look for what this expression is about. If the expression is exit, that means I intentionally put the exit as like a magic word that terminates the program, then I'm going to break the loop. So this break is going to get me out of the loop, the immediate loop. So the immediate loop here at this moment is the while loop, right? So there's no other loop. If I trace back here, there's no other loop than while. So I'm going to exit the while. That means I terminate the program. So if it's not the case, then you move on. So I'm going to search for the name and the function in the dictionary I defined before in the basic func variable. So I'm going to iterate over the keys and values of my dictionary of the function. And then if I get the same name as a function, then I compute that function value at the value that I currently have. Okay? Or if I don't find any function that I defined previously, then I look for whether it's an arithmetic expression. So I go for the names, and then if I get the arithmetic expression, so my expression I inputted is an arithmetic expression like plus minus, then I need another number to be inputted, right? So you need to have a pair of number so that you can carry out arithmetic operations. So I then try to get another input here, okay? So then try to get the value, taking the arithmetic between these two values. And also, I'm expecting to get a number after this point, but the actual expression, actual string that the user inputted may not be a number. If that's the case, then I just pass. So I don't do anything. So if I say I put it 1, string 1, and entered, and then I inputted plus, and then I should input another number that I want to add to 1, but I could have, instead of putting any number like 2, maybe I could put plus again. Then that's not an expression. That's not a valid expression, a mathematical expression that I can compute. In that case, I don't do anything. I just keep the value 1 and I repeat again. So going back to here. So that's basically the process of my calculator. So let me tell you what your additional task, if you're doing this for your first project, is. And then let's walk us through the whole process again. So this only shows you, whenever you run this program, the script that I just show you will just give you the prompt screen, the keyword here, and then doesn't show anything about how to use this program to calculate something. So you can make a help command so that if you type in help, then it shows you the documentation of how to use this program. And also you can try to implement more functions like this one. So it's a kind of exponential function, not really, but something that computes the value with the pair of number x and y. And also you can try to implement the tangent function or many other trigonometric functions if you want. And also you can try to implement nth root. Now in that case, you have to figure out, well, you can take the composite of these two functions, and also you have to figure out how to get the nth root of a value x, right? And also tangent is easy, but if you want to, let's say, try to get the tangent inverse. So if you want to implement the tangent inverse function into the calculator, then you have to think about how you could find the solution of that equation involving tangent. So it's not the only function that you can implement. You can find more functions you want and just put it into your calculator. Okay, so the third additional task is that sometimes, like in the Python, you type something and then you made a mistake, like a typo, then the error message says, did you mean this? So, for example, if you typed in sign instead of sin here, so this is the correct spelling, by the way, but usually the sin is the name of a function. So, however, even if you put the sign like this one, you still want to proceed your computation or let the user know that what's wrong. Maybe you could instruct the user to change the command. So make the program to print the correction of the input if any typo is found. So you have to handle the exceptions here. And that means your program will be a little bit longer than I just showed you here. So that's basically our second project. So I want to take any questions if you have any before we walk through the project. No question? By the way, where is the paper? Can I trace the paper? Okay, so anyone here read the paper? Check the paper again? So can you pass it to here? Okay, so this one is the last time. Okay. So let's make a calculator. So as I said, we need to define a function. I'm going to skip the part where we have exponential, log, and sine and cosine, because I need to write down all the definitions and implement it again. So instead, I'm going to define my add and subtract and so on. So I'm going to show you, but this is the one way you can do it. This is one way you can make addition, subtraction, and multiplication. I'm going to show you another way of doing it. So instead of using def keyword, since this expression is very simple, so you just take the two input and then outputs this number, right? So you can simplify it by add is equal to lambda x and y, x plus y. So you can do the same thing with this. So it works the exactly same as defining function using def keyword, but this is way simpler. So if it's not the case when you have lots of conditional statement inside of the definition of function, then this might be a more convenient way to define a function. So and then so arithmetics. So I'm going to define a data type called dictionary. So this is dictionary for arithmetics. So dictionary is a type of data in Python, such as a list or other type. And this type contains a key and value. So it's basically a dictionary. So if you want to find a dictionary, you need to find the word. You need to find the word, and then if you go to find the word, then you see what the word are meant to, right? The meaning of the word, right? So if I take a plus character, then I will make this as a key, and the value will be my function add, and same thing for other keys. Okay. So I'm not following exactly the same code that I put it in the slide, because I'm walk us through the entire project as if we are doing it from the scratch. Okay, so this is our basic basic ingredients here. So basically, I'm going to make a calculator only does the arithmetic operations. Okay. So I think your Colab also auto-completes the code, right? So I think it comes for free. I'm not paying anything for this. So probably if you're using Colab, then if you type something, then the rest of the code will be auto-completed. So I'm going to run this. So I didn't I didn't ask to print anything. So even if I run this, there's no print. But the information about my function and the dictionary are stored in the memory. So I'm now going to make a calculator program. So, okay, so I'm going to take the expression and this input is a command that takes an input, but I can let some character or some string to be printed before I input anything, before the user input anything. So this is the prefix that should appear in the input message, and then whatever I input there will be stored in the variable expression. So I'll try to convert the value. Okay, so here's a cheating way of making a calculator. So maybe I don't want to hide anything. So let me, yeah. Well, let me do this before I walk us through the actual project. So in fact, Python already has a calculator that actually interprets any string of the expression and try to compute as a number. So that's the eval command. So eval takes any string, and if the string is a valid formula, then it computes that value and then print out the value. So I'm going to do that here. So anyway, so I need an exception here. So if expression is same as exit, then I'm going to break the loop. But if it's not, then I'm going to print out this. Okay, so this is not the project that we are going to do, but I'm just giving you what this eval command do. So I'm going to run this. So it's very simple code. Oh, sorry. Yeah, I forgot this colon here. So, okay, so it says, okay, so you can see that there is a prompt here, which is same as this string. Then I'm going to put the expression of 1 plus 1. So this whole thing, 1 plus 1 will be, as a string, will be stored in the expression variable. And since it's not exit, it's not going to break the loop, but it's going to print the result of eval of this string. Okay, so I'm going to enter here. So it says 2. Okay, so actually it's I think it's very clever. Maybe it will compute x1 like this one too. Maybe not. Okay, so it's an error. Name x-space not defined. Okay, so maybe I can do something like 1 plus 2 square, something like this. Oh, it doesn't do anything. So maybe 2. Oh, yeah, it follows the Python grammar. So anyway, so what I inputted is a string of characters 2 hat 2 or 2 asterisk asterisk 2. So it's not a code, but this eval takes the expression as a string and then convert it into somehow some mathematical formula and then computes its value. But I'm not going to use this. So I'm just showing you there is a way you can convert your expression into a value. That's eval, but I'm not going to use this. But anyway, let's test out whether exit works. So if I put the exit here, then now the program was terminated. So before I put an exit, the program was keep running, so you can see that there is a spinning something here next to the button here, but now it's stopped. Okay, so instead of doing this, what we're going to do is trying to convert my expression. So I'm expecting that expression is a value or number. So that's what I'm going to try. And if it's not value error, then it means that the expression I inputted is not a value. Therefore, I should look for whether it's exit, then I break. If it's not, then I have to look for, what was it? Key value. Oh, no, value is used. So name and function in arithmetics items. So I iterate over all the items, pairing the key names and keys and values of that dictionary type. And if my expression is same as name, then okay, so I matched the arithmetics expression. I matched the symbol that I want to find with my arithmetic operation. So this function is going to be the arithmetic operation I need to do, but all the arithmetic operation requires two inputs. So I'm going to try to take the input of a new input here. So take the input again and try to compute the arithmetic operation. So try float. Did I mention? So let me go back here. I'm going to keep the same format here. Yeah, so it's similar anyway. So I try to compute the new function, I try to compute the arithmetic operation between current value and newly inputted value by converting my new expression into a value. And then I'm going to replace that result to the value that I stored here. Okay? That's what I'm trying, but if that does not happen, except value error. So this means that the float new is not properly converted. Okay, so the variable new is not an expression of number. So I'm going to print the invalid input. So you can do the same thing as I put it in the slide, just pass that case, or you can warn the user that you were supposed to put the number instead of expression or other string. So this is the warning message. Okay, then what we'll do is that after we okay, so when this is done, right, when this is done, I'm going to exit the loop. So here's the loop 4, right? So once I find the right expression, then I don't need to look for another expression that matches with the names of the arithmetics, right? So I can just simply end my searching. So I end my searching. Okay, and then after I done all of this, I have to print the result. I have to print the bell here. Okay. So actually, okay, so this is the entire code. So I'm gonna make sure whether this works. So I'm gonna put 1 and plus 1 equals to 2. And now 2 is here, and then I'm going to, let's say, minus 3. Oh, sorry. I think it's starting over. Okay, so I wanted to have, so if I have 2 stored here, oh yes, that's right. So minus 3, if I put the number here, it always replaced the memory here. So what I'm trying to do is, okay, so plus and 5 equals to 2, but I take the minus again, minus 3, then should be minus 1, right? X, oh, okay, so there's a misordering of here. So I want vel something here. Okay, so ordering should be current value operation with a new value, right? So this is the correct order. Okay, so let me exit again, then run this again. So, okay, so I put 1 here, and then I take the minus and 2, get the minus 1. So now minus 1 is the current value. Now I'm going to add 3 here, then I get 2. So basically, it's basically how the calculator, the GIST calculator works, right? With the one screen printing the number. So exit here. I'm going to let you see the code for a while so that this works for on your computer. So I'm gonna walk around, and if you have any question, raise your hand to see, and I'm going to help you. And also, if you have a trouble, then you can talk to your friends next to you to see if other friends are doing. Are you alone? Are you in the group? This group? Okay. How about you move to the group 7 so that you can work with her? That works? Okay. Anyone need help? No? Yes. Just a string. So this one, it's just the prompt prefix for the prompt screen. So I can just omit here, so you don't have to put anything here, but it's just a string that comes before your input area, okay, so that user know what's going on here. So this is just an indication that your line starts here. So you can put in something else. So if you don't like this, you can put the double arrow or any questions? Yes. Okay, so you see there are 2 input. So first input takes a number, probably, or symbol, and the next input is, if it's a symbol, then you need to get another number, right? So it doesn't print out the result until you input another number here. So if you put the plus, then you're required to put another number until you see the result. Oh, I think you forgot to print. Print has to be inside of this loop. So you have to take a tab. Yes. Okay, any other questions? So it's just a technical part. The real math part is when you have to implement functions using sequence or power series, whatever. Okay. Does not work?
Yes.
So it says arithmetics.
Multivariable.
So let's move up here. So arithmetics. No, this is not how I wrote. So when you define a dictionary, so you have to divide your keys and values by colon. Okay. Okay, any other questions? By the way, I'm going to save this file, and I already put the link to this file, so you can go to you can go to the Notion site with the link, and then you can see the same content as I see it here. Okay. If there's no more question, then we can move on to the next slide. Okay, so functions and continuity. So my plan was to introduce single variable function and multivariable function in a separate lecture, but I might change the plan a little bit, but so I'll try to mix those two. So when I get to the part when I have to explain differentiability, then I'm going to mix a little bit about the single variable and multivariable. But for now, let's talk about continuity. So now it's a little bit more to the content of multivariable function than the single variable function. So far, it's just the preparation of what we need to know before we understand the content. So, but I will start from the beginning, but most basics, because I want everyone to have the same backgrounds here, and also it's important to have using the same terminology for everyone. So what is a function? So function is a rule of assignment. Each element in the domain, the set called domain, here it's denoted by A, to an element in a set called codomain. Here it's denoted by the set B. So we define or we denote a function which sends an element in a domain A to the element in domain B as this symbol. So in an essence, function, in order to define a function, you need a map. Okay, so map is a rule of assignment, and you need a domain. So if you want to collect the essence of function, these two are the essence. But people usually forget about the information about the domain. They only talking about the map when they talk about the function. So for example, if you say function y equals to x, or let's say f of x equals to x, it's just a rule of assignment. It's not a function yet until you define what's the domain, what's the range of your value x. So you need two pieces of information to fully define your function. So these are the functions that you can think of. Well, that's not all, but in the calculus. So one type is single variable function, which has one real number for input and one real number for output. That's what you're probably familiar with. But from now on, we're going to talk about multivariable function, which takes two or more input, two or more real number as an input, or two or more output, real number as output. So I'll show you the example of these type of functions, multivariable function, later. But before, let me talk about another categorization of a function. So when I say a function is real valued, that means the value of function is the real number. That means the output is single real number. Okay? But if I say a vector valued function, that means the output is list of value, list of real number. It's not always mean that the output is vector. It's just a symbolic notation that vector valued, whenever you say vector, it's the list of two or more values, right? So when I say vector valued function, the output is two or more real numbers. So here are the examples. So this is the single variable function, which is a famous one. And also the two variable function, f of x, y equals to sine x squared plus y. It's a two variable function, but its output is real number, single real number. So it's called two variable real valued function. And the gxyz takes three real numbers as input, but it outputs a single real number. So it's called three variable real valued function. Okay. And look at the ct and suv here. So I can use any symbol for the input as I want. So here I used t as a single input, single real number input, but it has a two output, two real number as an output, as pair. So it actually maps the real number t to a two-dimensional point. So you can probably know what that is. It's a circle. So it's also called the parametric curve. And you can see that S takes two real numbers as input and outputs three real numbers. So each of three coordinate of this point, actually this is a three-dimensional point, is a formula of u and v. So you can consider each one as real valued two variable function. Right? So these are real valued two variable functions. Okay? So here we're going to talk about continuity, but then you have to talk about the graph first. So what is the graph? So whenever you have a function in a most general sense, then the graph is a subset of a times b. So a times b is a set of pair of points a and b, where a lies in a and b lies in b. So for example, if you take the r square, r times r, then it's a pair of two number x and y, both lies in r, right? So the same applies to a times b. So the graph is a subset of the set a times b, consists of this pair x and f of x. Okay, so you can imagine that, so I think there's a typo, this has to be a. So you can imagine x is the real number if f is a single variable function, but f doesn't have to be a single variable function. So if f is a two-variable function, for example, then this x is a two-dimensional point, and if f is a real value function, this is the single real number. So if you pair the two-dimensional point with the not real one more real number, then you get the three-dimensional point, and so on. So let's look at the example here. So if you have a single variable function, the graph is an object in two-dimensional plane in R2. So this lies in R2. Okay. So how about the graph of two-variable real-valued function like this one? So the graph is a set of point of input, which is pair of number, and output, which is single number. So if you combine these three numbers, the three real numbers, then they are the coordinates of three-dimensional point. So your graph of this function is object in three-dimensional space. It's an object of three-dimensional space. I didn't say it's a three-dimensional thing because the object is parametrized by two numbers, x and y. So it's actually a two-dimensional object in three-dimensional space. So we're going to walk through how to draw this object. So let's try to think about the graph. So how do we visualize a graph? So whatever we visualize, it can be only visualized in a screen or a piece of paper, whatever. That two-dimensional, it can only visualize in two-dimensional plane. Okay, so we need to convert whatever object we need to visualize is. We need to convert the information of that object into something that we can recognize on the flat screen. Okay, so on a flat screen in two dimension, only object you can distinguish each other are zero-dimensional object, which is the point, and one-dimensional object like line. Okay, so you might say two-dimensional object could be put into two dimensions, but let's say if you have a two-dimensional object which lies in the three-dimensional space, you cannot actually recognize this in a two-dimensional plane unless you take the projection. But when you take the projection, it's hard to recognize what the shape actually is, because if you're standing on a sun daylight and you see the shadow of yourself, then the shadow is not actually giving you the actual shape of yourself, right? It's only a projection. So anyway, the two-dimension is not the way you can project on the two-dimensional screen. You have to convert it into one or zero-dimensional object. So, and also another thing that you have to consider when you draw the graph is that the screen is finite. Whatever the medium that you try to visualize your graph is, it's finite. The monitor has a finite size. Everything is finite. So you have to restrict your domain of your function into a finite region before you take a graph. Okay. So for example, you can imagine the function from R to R, but you cannot graph this. Simply, you cannot graph this. Impossible. Like if you want to graph fx equals to x, you can imagine that it's an infinite line, but how do you draw the infinite line? It's impossible, right? So you have to bound your interval, the range of your point in domain. So there are 4 steps. First, you have to restrict your domain. Second, now another part, but I'll explain later. You have to partition your domain, because every graph consists of infinitely many points. You cannot draw infinitely many points. You cannot do anything infinite, right? So you have to make it finite by partitioning the point, partitioning the domain, and then evaluate the function value at each partitioning point, and then draw the line, because line is the object we can effectively draw on a two-dimensional screen. Draw the line that connects the partitioning point. So here is how you can draw the single variable function. For example, let's have this function as an example. I'm going to define the function first using lambda function I mentioned before. And then I'm going to restrict my domain, even though this function can be defined on every real number, sorry, not square, every real number except -1 and 2. So except these 2 points, you can define function value anywhere, but I cannot draw infinite many numbers, infinite many points, so I restrict my domain. So A is the left end and B is the right end. And then what I'm going to have to do is I have to partition my interval minus 2.5 to 2.5. So there is a command in the NumPy package called linspace that partitions the interval equally. And if I don't put any other then the left limit and right limit there, then it partitions. So what basically is it's partition, but what actually it returns is the partitioning point containing the left end and right end. It returns 100 partitioning point from A to B. Okay, 100 is a default value. So if you use 100 partitioning point from left to the right, then it means that you have 99 partitions. Okay, 99 sub-intervals. So here I partition it into 99 sub-intervals. 99 sub-intervals. And then I have to compute the function value at each partitioning point. So here X is a type of NumPy array. So it's an array of partitioning point, 100 partitioning point from A to B. If I put that into the definition of X, this directly goes to here, and in NumPy array can be computed arithmetically like this expression. So this y will be also be the same size NumPy array whose values are the function value at each x in the X array. Okay, and then I have an x and y array of x and y coordinates. I put that into the plot, which is a function that defined on the matplotlib package, and then I'm going to show. So if you use the Colab or any Jupyter notebook format, then you don't need this part. But anyway, if you don't use it, then you need to make sure that you try to show the plot. So let's try to let's try this out together and see what the result is. Where is code? Okay. So I'm going to define lambda x as 1 over x squared x minus 2. By the way, before I do that, I have to import NumPy as np, and I also have to import matplotlib. And then I'm going to set my interval from 2.5 minus 2.5 to 2.5. I'm going to set the partitioning point from A to B, and I'm going to compute the function value at each point in each partitioning point, and then I'm going to plot x and y. So as I said in the Jupyter notebook, this immediately shows you the figure. So you can check the figure on your own computer. And if you draw the graph, and you can see from the picture that it's a little bit chopped off, but you can still see what the characteristic of this picture. is that we all know that function, original function, is discontinuous at -1 and 2. However, this graph doesn't look like discontinuity at those points. So what it does is that it tries to compute and then try to connect all the points by lines, and then that's basically what it does. It doesn't understand what the discontinuity and what to do at this continuous point. So I'm going to make a little bit of adjustment here. Instead of using 100 partitioning point, let's use 101. So if I don't put this option here, then means that there are 99 partition. But if I put it like 101, then I'm partitioning the minus 2.5 to 2.5 by 100 partitions. Okay, so let's run this again. So now it's more like a real graph of this function, because you can see that there is a discontinuous. It's not connected anymore, right? It's a real discontinuous going on. So what's wrong? I mean, what's different? Why the first graph doesn't show the discontinuity, but this one does? The problem is it's not because the NumPy or Matplotlib understand the discontinuity. It simply says that if I use the 100 partition, then this -1 and 2 are actually in the array of x. So if I try to compute the function value at -1 and 2, the value would be inf or none, whatever. So there's no value assigned at that point. So if the value is none or inf, then this plot function cannot draw the line connecting the point. So it simply skip that part. So the line is skipped here because value is not defined. So anyway, so the problem is we need to, so there's, if you don't know the function, then you try to, so we know already what the formula of the function is. So that's why we're expecting to have this discontinuity and know that this is the right graph. But suppose that we don't know any information about f, but what we only know is what's the output of function when I put the number x. Then how do we determine the discontinuity or continuity? Okay, so we're going to discuss that later about the discontinuity and definition of a limit using the epsilon delta. So let me talk about how we draw the graph of two variable function. So in this case, real valued function. Okay. So as I said, the graph of this two variable real valued function is an object in three-dimensional space. So we're going to do the same, follow the same procedure. First, define a function like this, and then second, we have to restrict our domain. Even though this function is defined entire plane, I cannot draw the entire plane. So I will restrict the domain for x and y to be the interval from -1 to 1. So in the two-dimensional plane, it's region, the rectangular region from -1 to 1, like this one. Okay, here, -1, 1, 1. Okay, so I'm going to draw the graph of function over this region. And then, well, this is all the information I need. I need to know how, I want to partition the x and y interval. This is only all the information I need. How many partitions are there on the x interval and y interval? However, when you try to draw the graph of function, you need a point inside of the region. So all we did for taking this linspace is I know how to take the divisions here, subdivisions here, but it doesn't tell me anything about actual coordinate of inside of the region. What I need is actual coordinates of inside of the region, which is like say n squared number of points inside of the region. So these ones are, for in this case, 1 by 100, 1 by 100 array. It doesn't tell me anything about the 100 square number of points inside the region. So in order to get the 100 square number of points and the coordinate of those points, then I need to take a mesh grid. This is important when you try to graph the two variable function. So you're trying to get the grid of a lattice point. So this only gives you the one-dimensional point, right? I want two-dimensional point. Two-dimensional point has x and y coordinate for every point. So I need to take the mesh of this x and y coordinate so that I get all the coordinates inside. So then I'm going to store that in x and y1, y. After doing this, you get xx and yy to be 100 by 100 array each. Okay, so why do we have 200 by 100 matrix? Because each matrix represent x and y coordinate of the point inside of the region, which is 100 on the horizontally aligned, 100 aligned horizontally, 100 aligned vertically. Okay, that's why we need this much x and y coordinates. Then you compute the z values at every x and y coordinate of those lattice point. And once you get all the x and y and z coordinate of the points on the graph, then you have to put it into the figure, plot. But in Python, if you want to draw the three-dimensional figure, you need a little bit of preparation. So you have to take the figure and then add a subplot with an option of projection 3D, and then you use the plot surface to plot the three-dimensional figure here. So let's do it together and then see how it works. So here is the definition of function x and y equals 2x squared plus y squared. And I'm going to do a little bit differently than slide. So I'm going to do this. So it's kind of a nested assignment. So I'm going to assign y by the lint space, the result of lint space, and then assign whatever stored in the variable y to the variable x. And okay, and then let's try to take the mesh grid x and y, and then compute the value at each grid point, and then I'm going to plot this. I don't need this option. And this. So if you're using a separate IDE, not the Colab, then if you take the plot PLT show, then there's a window, the window appears, which you can rotate or zoom interactively with the graph. So here, it only shows you the picture as an image file. So you cannot turn this picture around. But you can see how it looks like. It's basically the same picture. I put it in the slide. So if you look closely to the picture, you can see there are lines, white lines are on the surface, and you don't have to count, but there are hundreds of lines on each side. So basically, you're taking 100 square points and try to make it into a nice figure that looks like a smooth function, smooth surface. But what really happens is it's not really a smooth function. It only looks like smooth because it's very dense. All the points are densely distributed. So if you zoom out each point, then it's a kind of a flat surface or polygon attached to each other. So for example, if I decrease the number of partition, so here default is 100, but let's say I want to put it as 5. So you can see what will happen here. So you can see that it's like now a polygon, right? So the smooth surface you see on the screen that you just saw on the screen is just because I increased the number of polygons that approximate the actual graph. So the actual graph is always in our head. It's an abstract thing. We cannot visualize this in a real life. All we can do is try to approximate the ideal graph using this finite object here. Okay, so let me give you the idea what happened here. So basically, the same idea happened because you have to understand this in order to do the third project. So the last one, this one is the final result. But there are ways to graph like this, but I did it without giving you the code. But the important thing is how you obtain, how how the Python plots the graph of function like this. What happens is first, when we took the value of z coordinates by doing this, we try to get all the points on three-dimensional space, which lies on the graph, like this one. So if you project those points onto the xy plane, then you get this grid points. So this is the domain of our function or the graph. And we put it into a grid points, and then each grid point, I computed the z value so that I can locate the points on the graph. And then I connect the two points next to each other by line so that each, the rectangle, it's not a rectangle, but it's a foreground, is representing the portion of a graph. So, and then what we did here is that at each foreground, you put the color inside. Just this one also gives you some figure, some idea what the graph looks like, but it's better if you can put the coloring here. So you just color the same color on each polygon here, each foreground here. So that's all. That's what you see here. So this is your example. Let's try to graph this function. So we have a domain restricted on this rectangle, and then this is our function. I'll let you do the program, and if you have any question, let me know. I'll walk around. So where's the paper? Can I get the paper back? Here? Okay. Did you guys know? So graph that function. If you don't know what to do, talk to your friends. Talk to your friends next to you. Colon, not equal. You have to put colon. Got the graph? Did you get the graph? Not yet? Okay, talk to your friends. Don't stare at the monitor. If you stare at the monitor, it's time to talk to your friends. You can use the link. I put it here. There's the link to the current Codap page. So if you go to this link, then you can see the same code that I put it here. So you can basically use the same code with a small adjustment here to graph this one. Are you done? Okay. Did you get the same scale? No? Okay, so if you try to graph, if you did the same thing, you're not gonna get the exactly same figure, same picture I see here. Yeah,
the default is giving a square image.
right,
So
yes.
it looks squished.
Right.
But the
So you have to figure out how you can scale the x and y z coordinate in the same size. So here, it's scaled with the same size, with the same scale. The length of x and y z the coordinate, this box is scaled the same. So that's why I see it longer in this side, shorter in this side. Oh, you got it.
Yes.
Okay.
This aspect ratio.
Yes. Oh, that one also works.
Yeah.
Okay.
You manually set the x limit and y limit.
Yeah, you can do that too.
Yeah.
I forgot actually how I got that picture.
I think you could manually set it as well, like manually set the limit and.
It doesn't work with setting the limit.
No, like
you have to set you can set the size of each
yes.
coordinate differently.
Yeah.
Yes. But this one also works?
Yeah, just
Okay.
set the aspect ratio.
Okay. Good to know. There are many different ways to do the same thing in Python.
That's the best.
Can it help? Are you done? Oh, okay. Oh, okay. Are you done? Okay. Did you draw the graph? Did you draw this graph? No? Why not?
I missed the class.
So how about you ask her? Did you draw the graph?
Oh no,
No?
not yet.
No, you did it. Why don't you teach her?
She got from assistant.
Hmm?
She got assistant from she didn't.
Anyway, well, she got the graph.
Okay.
How about you guys talk each other? to figure out how to do it. Okay, so you can basically use this code to get the same graph, but most of people got different from this. So I rescaled my x and yz coordinate so that this looks like a real how the graph really look like. But if you just use the same code, then it will scaled so that you get always the square square cube box. But if you see, if you don't use the same scale, sometimes it causes some problem. So you want to see the fluctuation, but somehow there's almost no fluctuation. But if you scale differently, then it looks like a big fluctuation. So it's good to know how to rescale. So I'm not going to do this question, but I'll put the one from this is one I got from the EMOD. So if you put the set aspect option here, then it's too small. Yeah, it's because it's already scaled the same. So let's see. So this is the option. This is the option that you can use to scale x and y z coordinate in the same scale. Okay. Did I make? I thought there was more. So let me see. Did I upload more? Okay, so I have more slide. So I want to go over a little bit more before we finish. So I'll let you do the program, the graphing part on your own after class. So let's talk about continuity. So we talked about the discontinuity of a single variable function, and we didn't conclude it yet. So I wanna continue our journey to the continuity here. Okay, so whenever you're looking at the function, so most of the time it's given by a formula, which is polynomial or exponential or logarithmic, sine, cosine, or the ratio of those functions. So you don't see much of the discontinuity here. But when you think about the function, what should comes in your mind is something like a black box. So it's because when it's the function is not that is pre-given, it's something that you have to figure out what that is. So for example, if you're doing a research on some phenomena, you want to model your phenomena with assumption that there is underlying function that governs the phenomena, but you don't know what the function is. So it's like a black box. But the phenomenon is there, so you know what's going to be the outcome when you put the input there. So the purpose of learning about the function is trying to figure out what the function is. So one characteristic that you can try to understand about function is what will be the limit value of that function when I approach my input into some certain point. So for example, if you have a single variable function, if the function value approaches to closer and closer to some value L, when I approach my x to closer and closer to C, then I can say the function is if the limit of function is L when x goes to C. The same thing applies to the two variable function. So instead of x, now we have x and y, meaning that it's a point in two-dimensional plane. So you can say the same way as the single variable function, such as if I move my point x comma y closer and closer to some point a comma b, if the function fxy, the value of function fxy goes to close and closer to the value L, then you can say, oh, the function has a limit L when x and y are closer to a comma b. So that's an intuitive notion of convergence and limit, but we want to be more rigorous how to define or prove this convergence. But before then, let's make a pictorial description of what I just said here. So when you try to think about the limit or convergence of single variable function, you want to find out a point or the value on the y-axis or in the two-dimensional plane when you're going to approach the point Q nearby the point Q. So here Q prime is the point near Q. I want to move my Q prime to Q and see if the value of function approaches to the certain point. So you can do the same thing with the graph of the function. So when you try to move your Q prime, which is the point in the domain interval, to Q, then the corresponding point on the graph of this single variable function approaches to P, right? So if that's the case, okay, I know that it's continuous. What about the two variable function? So here you have a graph, some portion of the graph of the two variable function, z equals to f(x) and y. And I also want to approach my Q prime, which lies in the domain of our two variable function, to Q, which is the fixed point. And I want to see whether the function is continuous. That means if I correspond this point Q prime to the point on the graph of a function, then if I make this Q prime approaches to Q, then the corresponding point on the graph also approaches to some point P on the graph, right? But the problem, the difference between the single variable case and the two variable case is that I have two different directions that I can approach to Q, from the right and from the left. But in the two variable case, there are infinitely many directions and infinitely many different shape of path that I can approach to Q. So there are two big differences. The difference is way bigger than you think. This is only finite number. Like you can only check two different method of approachment. But here you have infinitely many different ways to approach. So whenever you encounter infinite, don't try to do it by case. So there should be a different way of think about this approach. So here we have mathematical definition of a limit. How do we define the limit? So in the single variable case, this is how we define. Number L, here number L is called the limit of a function f at c if it satisfies this statement. It simply says if you have sufficiently small, even if how small this epsilon is, if there is a sufficiently small delta such that if your x lies in the delta range at the center C, then the function value has a function value and the limit L has difference less than the epsilon, which means that if you try to compute the error between these two values, that is less than the epsilon here. Well, that's the epsilon delta statement, and that's famous part in that's not just the famous. It's an important part in analysis, but you don't have to remember. You don't have to try to understand. I mean, you have to understand the core meaning of this. So I'm going to break down the statement here. The statement is mathematical, but the idea is very simple and it's based on common sense. So it says, look at the epsilon delta statement again. So it says I'm going to split into three parts. This part for every epsilon, and there is second part, there exists delta such that these parts. So this is A, B, C. Okay? So if I put it in this way, it says, okay, so I'm going to restrict A part a little bit smaller than this one. So it says, for every A, there exists B satisfying C. So what comes in the part A is epsilon. The positive is the condition that this variable epsilon should satisfy. And B is the positive delta, and also delta has to be positive. And C is this statement. It's a basic logical statement. If this happens, then this happens. So A implies B. So the epsilon delta statement of definition of this limit says that you need to find delta, making this statement true. So the core part is delta. So delta is very important part. So epsilon is given arbitrarily. It says for every epsilon. The core, the main part is there exists delta. Okay. So now forget about epsilon delta. So what is the meaning of epsilon and delta? So delta is the range of x. Delta lets you how far you can move from the center C. Okay. So in some sense, it gives you the range of x that you can measure your function value. And what is the meaning of epsilon? Epsilon is a bound. It is a bound between two values. This function value and the value L can be differ no more than epsilon. So you can think of this situation like this. I want to distinguish 2 points. Okay? As we mentioned before, let's say I want to distinguish 2 values represented by float type data. Okay? If you try to compute like 0 and 1/4 to the power of 1,000, you cannot distinguish these two in the float type because they are both same 0. However, mathematically they are different. What we can say about this situation is that 0 and 1/4 to the power of 1,000 is indistinguishable in the precision of the smallest number of the float data type. So it's about the precision. If you're looking at the two number within a precision threshold, then it gives you how small should be, or how big should be the difference of these two numbers should be in order to distinguish them as a different number. For example, if you're looking at the microscope has a precision. You cannot see, you cannot distinguish everything here, right? So if it has a good precision, that means it can distinguish small objects, but still it has a certain threshold. If you want to look at more and more, if a microscope doesn't handle this precision, then you cannot distinguish two objects, or you cannot distinguish the two objects is separated apart with a small distance which cannot be distinguished in the microscope precision. So anyway, it says that if you're given by a precision epsilon, then you need to take this much radius or less than this much radius in order to have a function value indistinguishable from the value L in this precision. And it states more. It states that no matter how your precision is, the epsilon is, if you take this small radius from the center C, then the value of function is going to be indistinguishable from L in the precision of epsilon. That's the limit. That's the limit. So no matter how small the precision is, let me repeat again because it's important. No matter how small your let's say precision of your data type is, if you take a close enough point to the center or the point C, then the value of function that you're going to compute, whichever point you're going to plug in, even if it's less than delta range, delta radius, then that value is going to be served as the same as L, because you cannot really distinguish those two numbers in that precision. So that's basically the idea of a continuous, of the limit here. So what is the, okay, so let me, here, okay. It's a technical part, so I'm going to skip this for now. So let me just briefly mention what we're going to talk next time. So we're going to generalize this idea to talk about the limit of two variable function. But however, as I said, the big difference is that in the single variable function, I can only take the two numbers in the domain and then take the difference because that's the distance between 2 points. But in the two variable functions, I cannot just take minus of these 2 points. Doesn't make sense because you have a point. So instead of taking the subtraction of these 2 points, which doesn't make sense anyway, I'm going to take a distance between these 2 points. And if this is the point that I want to figure out the limit, then if I take any points nearby this center, I'm going to take the distance and how far could my points could be so that my function value is close enough to the desired limit. So that's the idea of a limit of two-dimensional point. So it's not the way we worked as the way we worked for the single variable function by taking the limit. When we take a limit in the single variable function, we try to take the x to the point C in direction of right or left, but that doesn't work in the two variable function case because you can approach to the point in infinitely many directions and also infinitely many shapes. So we're not going to approach, we're not going to understand the limit in this way. Instead, we're going to take the definition of the limit, epsilon delta statement, into the statement for the two-dimensional case, and then work from there. So that's the material that we're going to cover next time, and we're gonna meet next week, right? So Oh, by the way, I have a important announcement. So there are some people, before we end, there are some people who wants to do the neural network. So I'm going to give I'm going to held a meeting next Thursday, right after our holiday season, to talk about the neural network project. Okay, so I just had a meeting yesterday with the person who wants to do the heat flow project, but I'm gonna do the same thing for the people with the neural network project. So I'm going to open up mentorial session, and if you want to participate, you can join there by registering, and we're gonna see there on Thursday. So make sure, don't forget to come to the mentorial session, because this is going to be the final announcement, because we don't have a class on Wednesday. So have a good holiday, and then see you on next week.